Imagine yourself 10,000 meters above sea level, comfortably seated in a 380-ton commercial airplane. Yes, 380 tons. You take your drink from your glass, put a magazine back in the seat pocket in front of you, and remain there, suspended in the air, as if it were the most natural thing in the world. But think for a moment. You are inside a metallic structure that weighs the equivalent of 180 passenger cars, flying at 900 kilometers per hour over oceans and continents. If someone, 500 years ago, had said that this would be possible, they would have been considered crazy. But the question that almost no one asks is, how on earth does such a heavy object manage to stay in the air? How come physics doesn't seem to be working? You would think that something so heavy should plummet immediately, falling like a stone, disappearing into the clouds below. But it doesn't fall. It rises, floats, traverses the sky with a grace that defies all intuition. Today we will reveal this extraordinary secret. You will not only understand exactly how airplanes manage to fly, but you will also see the most brilliant and contradictory piece of engineering that connects 17th century physics to your vacation flight tomorrow. Before flight, it was impossible. Absolutely impossible. For millions of years, humans observed birds and thought, why can't we do that? People jumped from towers with wings made of feathers. They leaped from cliffs with wooden structures strapped to their arms. Some supposedly managed to fly for a few seconds before crashing to the ground with a final thud. The frustration was real. There was something profound about the impossibility. It wasn't just a matter of ingenuity or creativity. It was as if nature itself had established an immutable law. Humans don't fly. Period. This law was so strong that until the 18th century, most scientists believed that flight would forever be impossible, even with hot air balloons being invented in the late 18th century. Controlled aviation, true flight with heavier-than-air machines, remained a fantasy until 1903, until the Wright brothers. But the question wasn't how to fly anyway. The question was, how to fly with something that is heavier than the air surrounding it. How do you make something made of metal and gasoline stay suspended against the strongest gravity? This urgent need to understand the flight of heavy machinery led scientists to discover something so elegant, so counterintuitive, that it would change the history of humanity forever. The solution wasn't a complicated mechanism. It was simple principles combined with extraordinary precision. And it has a name, Bernoulli's principle. But before understanding Bernoulli, you need to understand what really happens when air touches an airplane wing. It's not magic, it's fluid dynamics. It's a truth so fundamental that it goes unnoticed every day, but it literally underpins every flight that has ever taken place. The aviation system, as we know it, consists of 5 basic elements that work together in perfect harmony. First, we have the wing. An airplane wing is not flat and simple. It has a very specific shape called an airfoil. This shape is not arbitrary. It was designed after decades of wind tunnel testing, complex mathematical calculations, and a wing has a side that is more rounded at the front, a curvature that extends across the upper surface, and a lower surface that is straighter or less curved. This is the second element, precise geometry. When air flows over this wing, it doesn't flow uniformly. The air passing over the upper surface has to travel a greater distance because the curvature is greater. The air passing over the lower surface travels a shorter distance. This means that the upper air moves faster than the lower air. Here's the key point. When air moves faster, its pressure decreases. This is Bernoulli's law. Higher pressure below, lower pressure above creates a pressure difference that pulls the wing upwards. This upward force is called lift. But lift doesn't arise solely from the pressure difference. There's a third element involved, the angle of attack. The wing isn't completely parallel to the airflow. It's slightly tilted. This tilt means that the air hitting the underside of the wing is deflected downwards. By Newton's third law, every action has an equal and opposite reaction. If the wing pushes the air downwards, the air pushes the wing upwards. Therefore, we have 2 forces working simultaneously, Bernoulli's pressure difference and the Newtonian deflection of the air. Both contribute to creating lift. But lift alone isn't enough. You need to move the wing through the air at speed. That's the fourth element, the engine and propulsion. Airplane engines, whether modern turbojets or old piston engines, do only one fundamental thing. They move the airplane forward at speed. The faster you move the wing through the air, the more air passes over it. The greater the pressure difference created, the more lift is generated. It's a direct mathematical relationship. Lift increases with the square of the speed. This means that if you double the speed, you quadruple the lift. Therefore, when an airplane takes off, it accelerates on the runway, and at some critical point, when the speed is sufficient to generate lift equal to the weight of the airplane, it leaves the ground. It doesn't explode into the air. It ascends smoothly because the forces are in perfect balance. And here we come to the fifth element, control. An airplane doesn't just fly. It flies with precision. It climbs, descends, turns, stabilizes. This is possible thanks to the ailerons, elevators, rudders, and flaps. These are small control surfaces on the wings and tail that modify airflow, altering lift on different parts of the aircraft. A raised aileron reduces lift on that side of the wing, causing the aircraft to turn. A raised elevator increases lift on the tail, causing the aircraft to climb. An extended flap increases both lift and drag, allowing for safer takeoffs and landings. But here's the real secret that most people don't understand. A 380-ton aircraft can fly because every part of that machine was designed to distribute that weight extraordinarily efficiently. A Boeing 747 has a wingspan of 60 meters. That enormous wing is generating lift along its entire length. Multiply the lift generated per square meter of wing by the total wing area, and you get enough total lift to lift the entire weight. The math is simple. Lift equals weight. The aircraft flies. Lift greater than weight. The aircraft climbs. Lift less than weight. The aircraft descends. It's like a perfect tightrope walker, but there are added complexities to the mix. The aircraft's structure needs to be simultaneously strong enough to withstand these immense forces of lift and control, yet light enough not to add unnecessary weight. Engineers use special aluminum alloys, carbon, composite materials, and structural engineering so sophisticated that every gram of weight is accounted for. One screw too many, and you lose fuel efficiency. One screw too few, and you compromise structural safety. Therefore, airplanes are built within such precise mathematical margins that they seem miraculous. Although the Wright brothers' original designs have been superseded by jet-powered reaction technology and computer control systems in the 20th century, the fundamental principle remains the same. The wing continues to function exactly as Bernoulli described in 1738. Air flows over the curvature, creates a pressure difference, and lift is generated. Modern Airbus, A380s, and Boeing 787s fly according to the same laws of physics as the fabric and wood airplanes of the early 20th century. Technology has changed. Materials have evolved. Control systems have become computerized. But the physics remains constant and elegant. Today, airplanes weighing hundreds of tons fly with a safety that is statistically safer than driving on the highway. A modern jet engine creates over 70,000 kilograms of thrust, moving the plane to speeds where the lift is so great that the plane could climb indefinitely if it weren't for decompression. At high altitude, fighter pilots can create enough lift to make the plane perform maneuvers that defy intuition. Inverted flights, where the pilot hangs upside down, held only by the lift generated by the inverted wing. High speeds where the air becomes so dense that it creates entirely new challenges. But in all cases, the basic principle remains: movement, geometry, pressure, difference, lift. The next time you board a 380-ton airplane, when you feel that extraordinary moment when the main wheel leaves the ground and you are gently lifted into the air, remember that you are not defying physics. You are being carried by physics. Gravity pulls you down with a force of 380 tons. But the wing, through its perfect geometry and the speed of movement, generates a lift force that is slightly greater. The difference between these two forces, which may be only a few kilograms at the beginning, is enough to lift you off the ground. This small difference, multiplied by human ingenuity, the precision of modern engineering, and the immutable beauty of the laws of physics is what allows you to be sitting 10,000 meters up, enjoying a drink, contemplating the world below, in perfect safety, because airplanes don't defy gravity. They understand it, and when you understand something so deeply, it's possible to fly with it, literally. If you enjoyed this revelation about how airplanes manage to fly, have you liked and subscribed to the channel? If you haven't yet, now is the perfect time. Turn on notifications so you don't miss future videos like this one, where we unveil the secrets of the simple things we see every day. And leave your comment below. What was your theory about how airplanes manage to fly? Before watching this video, were you convinced it was magic? Did you think there were helicopters hidden in the wings? I want to know what you thought. But before you go, click on the video that's appearing on your screen now. It's another curiosity you probably never wondered about, but it has an explanation just as fascinating as this one. So click there, continue the journey with us, and let's unravel another mystery of the world around you.